那我们下面就进行我们今天非常精彩的这个主题报告环节。下面我们进行第一个报告。因为网络一点原因呢 ，Judy Perrow 暂时没法上线，所以我们第一个报告呢改为 Ruslan Salakhutdinov 的报告。下面我们有请这个卡耐基梅隆大学教授 Ruslan Salakhutdinov， 他的报告的主题是 Integrating Domain Knowledge into Deep Learning。welcome.
Thank you.
Ruslan Salakhutdinov， 卡内基梅隆大学教授，加拿大统计机器学习研究主席，微软学者和斯隆奖获得者，主要研究领域为深度学习、概率图模型和大规模优化，师从 Jeffrey Hinton， 是简知、深度编码等著名深度学习方法的提出者。他于2009年获得多伦多大学的博士学位，随后又在麻省理工大学开展为期2年的博士后研究。2016年入职卡耐基梅隆大学，同年获得英伟达人工智能先驱奖，并加入苹果公司担任 AI 研究总监。目前 Ruslan 已累计发表学术论文300多篇，引用上万词，是深度学习领域年轻一代领军科学家。
Hi Ruslan, can you share your screen?
Yes. Just 1 second. Let me share my
nice
screen.
To meet you here.
Thank you very much for the invitation. Can you see my screen?
Yes.
Yes, we can see it. Great.
Okay.
Let me just make the sound just a little bit. There it is.
Okay.
Sounds good. Okay. Well, thank you very much for the invitation. I thought that I'll talk about some of the recent work that's been happening in my lab at Carnegie Mellon University. So let me start that a lot of my work focuses on various aspects of deep learning, and you've seen impact of deep learning in speech recognition, vision, recommender systems. A lot of my recent work is also focusing on language understanding, and we also see some examples of drug discovery and medical image analysis. And really, if we think about, what do we want to do, how do we want to build AI, we're really interested in building algorithms, computer algorithms that can, see and recognize objects around us. And I'll show you some examples of that. Understand human speech, reason and understand natural language, be able to navigate it honestly, explore and plan, and in general display human-like intelligence. So one of the key challenges that we're facing today in machine learning and deep learning in particular is these 4 things that I've listed. One of them is the natural language understanding and reasoning. So I'll give you some examples of how can we build question answering systems, for example, that can take domain knowledge into account. Another area of research is embodied AI, or you can think of it as applications of reinforcement learning and control. And again, I'll show you some examples of that as well. And how do we incorporate domain knowledge? How do we incorporate structure into these models? And of course, there's also a lot of work in the area of multimodal learning, semi-supervised learning, self-supervised learning. So I'll mention some of that as well. Okay, so let's dive into one specific aspect. A few members of my lab at CMU have been working on looking at language understanding and incorporating domain knowledge. Okay, so when we think about a lot of deep learning models, we typically think about supervised learning, right? We typically think about an input that goes through some neural network and then produces the output. So for example, if I say my input is this image, I want to recognize it as a cat, for example. Machine translation is another big area of research where I give you a sentence in French, I want to translate it into English, for example. Right? But, when we think about these models, like if I ask you the question, which coronaviruses are known to infect people, there are multiple answers, right? There is COVID-19, there is SARS, for example. And this is where using what we call domain knowledge is going to be very important, because answering these questions is fairly difficult, right? We have to get this information from somewhere. could be in the forms of tables from the web, maybe articles, news articles, or Wikipedia articles, perhaps even tables. So how can we do this? And that's a pretty challenging problem. A lot of work is taking place in this space, especially in the industry. A lot of personal assistants. When you look at Google, when you look at Cortana, Alexa, Siri, this is something that's is driving. How can we do that? It's a very difficult question. Obviously, the data is heterogeneous, which basically means that it comes from text, it can come from images, and can come from ontologies. How do we reason? How do we collect this information and also, aggregate this information across different sources? And, how do we make use of what we call weak supervision? Instead of labeling every single question with an answer, perhaps we can have weak supervision. Maybe we can provide what's called, just a few labels, or maybe not specific labels. So all of these questions are the key challenges to building these systems. Okay, so when we think about these systems, we typically think about knowledge bases. So for example, we can go on the Wikipedia, we can collect important concepts, perhaps think of them as entities, like words or sequence of words. And we can think about perhaps building a knowledge base. And that's traditionally how, information technology companies have been building these big knowledge bases. For example, Google search is relying a lot on these knowledge bases. And then we can also collect information that relate these different, what we call facts about entities, right? So for example, we can say diabetes is treated by chromium, or diabetes has an effect on certain things, right? And so we can build this knowledge base, and a lot of these knowledge bases are also curated by humans. And when we think about these knowledge bases, the question is, how can we use this knowledge base in combination with deep learning models to build something useful, right? So if I give you the question, there is a process that's called entity linking, where we're trying to parse the question and figure out what the question is asking. And perhaps we can find what we call a question subgraph. So here we're retrieving about 50 Wikipedia articles. We're retrieving about 50 different entities that the question is asking about. And then we use what we call the graph comprehension via something that's called graph convolutional neural networks to provide the answer. So this process is sort of a way of combining deep learning and the knowledge base. So how we do it exactly? Well, the idea here is that we can augment our knowledge graph with text. So for example, if I ask you the question, who voiced the dog in the Family Guy? So Family Guy is a show, it's a cartoon show. And if I ask you who voiced it, well, I can identify the mention, which is Family Guy. I can also look at perhaps Wikipedia and identify certain facts about, Family Guy. And then I can basically build a knowledge graph together with these sentences that I extract from Wikipedia to be able to provide the answer, right? So you can think of this research as a way of taking your knowledge graph system and augmenting it with this textual information. And the way that we do it is you basically say, well, here's the question. We can use recurrent neural networks or any other way. So for example, we can use transformer architectures to get the representation of the question. We can also look at the knowledge graph, and here we're using graph neural network, what we call the convolutional graph neural network, to get the information about entities as well as dimensions. And this is a little equation here. I'm not going to go too much into the details, but it's essentially a way of combining information that's coming from the text and the information that's coming from the knowledge graph. And the idea here is that you can fuse this information together in order to be able to answer questions correctly. And in many cases, the reason why we want to do this is because knowledge bases, in many cases, are incomplete. So we want to be able to use a lot of information from text, from web, or what sometimes we call unstructured data to get that information as well. right? So here's some results where we basically show that across multiple data sets, this idea of combining text representation with a knowledge base can actually improve performance of your system. So here, what we call knowledge-based completeness is how large your knowledge base. So in many cases, if your knowledge base is not very large, using textual information gives you a lot of gain. Now, when we think about this particular structure, right, so this is the idea of given the question, we try to understand what the question is asking. We try to find the information in the knowledge base together with a Wikipedia article, and then we're going to use deep learning models, the graph neural networks, to be able to answer the question. But what about more interesting questions? So this is a fascinating area of research because it actually is quite difficult to solve something what we call complex multi-hop questions. So let me give you an example. Imagine I ask you the following question. Where is the company which manufactured Voglibos headquartered? So Voglibos is a specific type of drug, right? So in order to answer this question, I need to be able to answer two questions. I need to be able to answer the question, which company manufactures this particular drug? And then once I know the answer, I can ask, where is this particular company's headquartered? Right. So in this case, you can get the information that Voglibos, this particular drug, is a product of Takeda Pharmaceutical Company, is Japan's largest pharmaceutical company. And then if you say where this particular company is headquartered, you can basically say it's a Chuku, Osaka, right? Okay, that's fine. But then the question is, internally, we don't know the answers to these intermediate questions. And so that's why this is sometimes called multi-hop question, right? Because you need to be able to get this unknown information and be able to connect perhaps different sources of data to different Wikipedia articles to be able to answer the question. And so in many cases, if you look at personal assistants today, if I ask you, anytime I ask a complex question, a lot of personal assistants like Alexa or Siri, they fail. And in many cases, they fail because they cannot solve this multi-hop reasoning, right? So let me talk a little bit about how we can actually solve or at least make a step towards solving this problem. And now you can imagine that sometimes I can ask questions that are, three-hop questions. So in order to answer it, I have to answer, a sequence of questions internally. Right? And so the question is, how can we do it when we don't know these intermediate steps? And the idea here is, there is a prior work, but the prior work doesn't generalize, and it's typically fairly slow. And the question is, can we do it in an end-to-end fashion? Can we do it with deep learning models so that we can actually backpropagate our model through the entire architecture? Can we do it efficiently, in the sense that we want to be able to answer these questions in real time? And can we make it compositionally, which basically means that it's a composition where I'm answering the first hop and then the second hop and then the third hop. And this idea of using domain knowledge and compositionality will come back as I talk through the rest of the talk. These are very important concepts. So let's see how. So here's the system that we've built. Actually, my student Boan Singa, who's going to be joining Duke University as a faculty, built this system. So this is a real-time system. Let me show you again. So if I ask you the question, which company founded by Steve Jobs was based in Redwood City? And this a model running in real time, you can see it's analyzing 5 million articles. It's running on a single machine, so it's a single CPU machine. And here, the correct answer is Next. So that's a company that Steve Jobs founded that was based in Redwood City. And Steve Jobs founded multiple companies, right? He founded Apple and Next. But only Next is the right answer. And so here, the idea is that at the first stage, you have to figure out how many companies Steve Jobs founded. And so you see the first paragraph here, it shows that he founded Apple and Next. And then the second paragraph, the truth paragraph, actually gives you the information where the company next was based, right? Or which company was based in Redwood City. So in other words, you have to find these two separate pieces of information in real time, aggregate this information, and provide the answer. So this is the system that we've built. The paper is out. You can look at the code. I think we're going to be releasing the code so you can use it in your own research. Or you can also use it for industrial applications, I believe. So how do we do this? And the idea is fairly simple. What we do is we do something that what we call a follow relation. And the idea is the following: given the set of entities, so we can think of entities as company or Vogelboss. So we can think of them as specific nouns. Then we're going to follow relation R. So given the entity, we follow relation R, we get the answer, and then we can follow another relation R and get the second answer, right? And then we arrive at a set of entities or the set of answers. So let me show you here what I mean by that. So X here would be the name of the drug. And the relation here would be manufacturer. So, based on this, we can say who manufactures this particular drug. And that will give us the first set of entities, so the first set of answers. The second relation would be headquarter location. So once we know a set of entities who manufactures this particular drug, then we're going to say what's the headquarter location, right? So you can say we're going to build this hierarchical model where X, we're going to follow relation R to give us a set of answers, and then it's going to follow relation 2 to give us the final set of answers. And so this is kind of the idea of, parsing and using this sort of information flow, being able to answer multiple multi-hop questions. Okay, so what's the relation following like? Well, one thing you can do is you can say, well, if I have an entity, then I can maybe build a matrix. Think of this as a matrix, which we call has character. So which of those mentions has character? And then the answer would give you the answer. So if you think about this particular approach, which was published in 2019, you can think of this W as your knowledge base, as your explicit knowledge base. So imagine, this is W is your particular relation, and you can build a lot of these matrices and essentially, apply these matrices to be able to provide you the answer. So this is basically equivalent to building an explicit knowledge base, right? Instead, what we do is we build a virtual knowledge base based on textual information only. So imagine that you go to Wikipedia and you collect entities. So entities could be, the names, nouns. In our setting, we have over 5 million entities. And mentions would be, in our case, these are sentences that we extract from Wikipedia, for example. And in our case, we've been looking at about 100 million mentions. So think of them as sentences. And again, think of mentions as sort of information that's coming from unstructured sources of data, like Wikipedia, for example, right? So now we can build the entities, we can build the mentions. And so what do we do with them? Well, then we can build this idea of follow relations. What we can do is we can say, well, if we have an entity, for example, Family Guy, and we have a relation, which is dog in the show, then what we can do is we can expand our entity into the set of mentions. So we basically look at all the Wikipedia article, all the sentences that mention that particular mention, like Family Guy, or that particular entity, like a Family Guy. Then we're going to filter those mentions based on the query or based on the question, right? And this can be done using the scoring, the dot product information. And then we're going to be combining different scores across different mentions to give us the answer. And the key idea is that all of these operations we can do very efficiently using basically dot product operations. So now I'm skipping a few technical details here, exactly how this is done. Essentially, these sentences are encoded using transformer architecture to get us the low rank representation of these mentions. We also train, the representation of mentions, again, using transformer-like architectures. But, at the end of the day, it's a sequence of operations that allow us to get the final answer. And so, again, these are just the representations that we get. We basically expand our X to the co-occurring mentions. So we search through all the sentences that talk about a particular mention. Then we filter mention based on the query. And again, this is where the language piece comes in. This is where the transformer architectures come in specific ways, the technical ways that we're actually constructing this matrix T. And then we're combining these scores. So we're taking all of these mentions that we get after filtering stage, and we project them back into the entity space, and that gives us a set of answers. What's interesting about this architecture is that you can see it's modular, which basically means that if we have two follow relations, we can just construct these matrices on top of each other. And this particular architecture, we can also backpropagate through the entire set of matrices in this case, or through the entire set of operations. And so here, it's efficient because it's basically polylog. It's closed on decomposition. It's differentiable, so we can actually train it in the end-to-end fashion, right? And exactly how we do this is through doing soft entity linking. So given the question, we find entities. Then we use transformer architectures to give us the representation of the relation 1, and the transformer to give the representation of relation 2. And essentially, we basically getting the answer. We can backpropagate through this entire differentiable architecture. So to me, this is interesting because here we're basically building these knowledge bases, but these knowledge bases are not built explicitly and curated by humans. These knowledge bases are now built based on Wikipedia, based on sentences, right? So it's actually pretty interesting because now we can build very large-scale knowledge bases. And it's because it's an end-to-end architecture, we can actually learn this architecture in an end-to-end fashion. And just to show you just very quickly some of the examples that, when we look at multi-hop questions, we can actually do much better than existing models. But what's also interesting is that because you're using these differentiable operations and because you're using them in a very efficient way, you can actually do about 19 questions per second. This is using 2-hop and using 12 questions per second if it's 3-hop questions, right? So here's another example running in real time. What's the shape of the family of viruses containing coronaviruses? It's looking at 5 million Wikipedia articles. It quickly finds the right answer and gives you the correct answer, in which case it is spherical, right? So there are numerous applications in that space. And this kind of brings us to this notion of, okay, we sort of started looking at the knowledge bases, right? And maybe perhaps we can construct them explicitly, or perhaps we can look at Wikipedia and try to construct them implicitly. But the question still remains: how can we incorporate human knowledge into our systems? How can we incorporate common sense? And how do we basically make this integration more efficient? So that's a big sort of area of research, and it's quite, in my view, I think it has a lot of potential and a lot of applications. So let me quickly dive into the second part of the talk, because I wanted to also say how this natural language jointly works together with reinforcement learning and deep reinforcement learning and what we call embodied AI architectures. So a lot of this work is also based on the work of my PhD student, Devendra Chaplot. So let me kind of mention that, we've talked about language and question answering and knowledge bases. In the reinforcement learning domain, in many cases, we want to be able to learn behaviors, right? We want to be able to map a sequence of observations, what we see, to a sequence of actions to achieve a particular goal, right? And when we think about physical intelligence, we typically think about an agent. An agent observes, let's say you have a robot in your house. It observes an image, it takes an action, and the agent obviously needs to move in the world physically. And the current actions can affect future observations, right? If I choose to turn left, I'll see something different than if I choose to turn right, for example, right? And it also requires some spatial and semantic understanding of the scene. And, typically, for example, if I want to reach a particular location, let's say my agent needs to go to the bedroom or it needs to go to the kitchen. If it achieves that goal, I get the reward. So here we have an observation. Typically, you get passed through the deep neural network, you get a set of actions, and then you get a set of rewards that telling you, was this a good action or was this a bad action, right? And then you can back propagate through your architecture to find the right set of actions. And this is what we sometimes call end-to-end reinforcement learning. And there's been a lot of work in machine learning and deep learning communities as building these end-to-end reinforcement learning systems. And actually, they work pretty well. Now, let's say, there are multiple things you can do. Let's say for a point goal location, I want to be able to navigate to a particular XY coordinate. A more challenging goal is the image goal location, where I show you an image and I want my agent to find that particular image. So I show you TV, I want my agent to go to the TV, for example. Object goals, if I specify where I need to go, and this is where the language comes in. If I specify the instruction, how to navigate to a particular location, that becomes more challenging because you need to understand the language aspect of it, right? So this is where the language understanding also comes in. And in the context of language understanding, there's been a lot of work in terms of, building systems that can, understand what does it mean, what different objects mean, and so that they can navigate to the right location, for example, to the right object. But when we think about these tasks, these navigation tasks, right? One of the biggest problems is this notion of exploration of the environment to find the right goal. So how do we explore the environment efficiently? So for example, let's say you have an agent, your personal robot in your house. The agent needs to go around. As it goes around your house, it needs to explore efficiently to figure out what's going on in your house, right? For example. So how do we efficiently explore unseen environments? And, in many cases, if we look at the end-to-end systems, right, it's very difficult to build efficient end-to-end systems because they're simple and efficient, and they typically have poor generalization. And, what we need to do is we need to incorporate the strength of learning, but we also need to build modular systems. We need to incorporate some domain knowledge or the prior knowledge, and perhaps building hierarchical systems that would allow us to, figure out how to solve this problem more efficiently. Let me show you an example. This is a real robot, so that's navigating in my student bedroom. And here's what the navigation looks like. Let's hope that the keynote doesn't fail. Whoops. Let me see if it... for some reason, the keynote, doesn't want to... but here's... I'll show you more examples of this. But this is just an example of showing a real robot navigating in the real environment and building the map. Well, let me skip through that, and I'll show you down the road how it actually works. And so how it actually works is what we call the neural SLAM, simultaneous localization and mapping system. So you get the observation. There is a neural SLAM model that essentially builds the map of the environment. Then we have something what we call a global policy that specifies the long term. Where does the agent need to go? Based on that, we essentially have a planner. And a planner basically tells us how to reach, how to plan a path to reach the goal. And then there is something what we call a short-term goal, which is just navigates a couple of meters in our case. And then there is a local policy that actually takes an action, so executes the agent. So you can think of this architecture. It's a hierarchical modular architecture where the neural SLAM builds the map, the global policy learns where the agent needs to go, the planner plans the path, how to get to this goal, and the local policy specializes how the agent should move, short term, how the agent should move in the next 2 meters exactly. Right? So here's an example of a robot navigating in the apartment building. This is called the Gibson environment, and building the map of the environment, right? So it's an unknown environment. It's the first time the agent sees this environment, and it's trying to navigate and explore the space efficiently as possible, right? So here's another example. It's a generalization to a slightly different environment, right? And so you can see it's just based on the visual information, the agent learns how to navigate and how to map the environment. So if we look at, for example, very quickly at the point goal navigation, right? So these are navigations where we give the coordinates. We will tell the agent, go to the XY coordinate, and the agent just needs to figure out how to get there. We can also, this particular example won also the Habitat 2019 CVPR Habitat Challenge. This is the challenge where your goal is to navigate to the coordinates as fast as possible. So you're given a particular location you need to get to. You're given an unknown environment, an unknown apartment building, and you need to get to the coordinates as fast as possible. And so here, what the metric here is what we call SPL. It's basically the success rate as well as how efficient your path is. But let me also maybe spend the last sort of 10 minutes also pointing out to another task, which I think is also a very interesting and challenging task, which is the image goal location. So imagine that I give you this environment, right? And your agent, I give you this particular image. This is the image of the stove, right? And then the question is, which path would you take to find this particular image? And this is where, your semantic priors, your understanding of the scene, it becomes important. Because I think in this case, path number 2 would be the most optimal path to take, right? You wouldn't go upstairs to look for the kitchen because kitchens are typically located on the first floor. So how can we use the visual information to build kind of robust systems that can use this information, right? Most of the existing navigation algorithms struggle to do so, struggle to understand. So if you look at a lot of robotic systems, traditional robotic systems, they don't use this visual information. And so the idea here is that if we can actually build the topological map of the environment so that we can understand where the living room is, where the dining room is, where the kitchen is, then perhaps we can do a better job at figuring out and navigate in this environment. So we've started looking at the topological graph representation, right? So here we're basically saying nodes now represent areas. So think of a bedroom or the kitchen. We can think of what we call ghost nodes as representing the unexplored areas, the areas that we need to go to. And the regular nodes actually represent areas that we've visited. They represent explored areas. Right? And so, for example, if my goal image is to go to a particular location, let's say in the bedroom, then based on that, I'm going to choose a particular path to go to that location, right? And so here's just an example of kind of, expansion that we use based on this topological representation. Let me show you, and when we think about these nodes, the relative position between these nodes is what we can learn, and we can kind of store the spatial information between these relative nodes. And so when we think about this neural topological SLAM, we basically have a module that updates the topological map as it receives observation. So we actually build the topological structure of the map. And then the rest remains the same. We have a global policy, we have a plan, and we have a local policy so that the agent actually navigates. This is compared to kind of a metric setting or neural SLAM setting that I've talked about before. Yeah, sorry about that. I just got, for some reason, I got disconnected. Let me just kind of, point out that this is sort of, so what we built is we built a global map, the topological structure of the map. So we have the agent location. We propose the nodes that we need to go to. We choose based on that information and based on the image information, we choose where we need to go next. And after we get there, we expand, we build other sets of nodes and so forth. So we actually, as we go and we navigate, we build this topological structure of the environment, right? Here's kind of like the visual representation of what it actually looks like as the agent navigates through the environment. and building the topological structure of the environment. Here's another one. So this is, again, this is done in a Gibson environment, which is an environment that was built by UC Berkeley and Facebook. And you can see that, the agent kind of builds the map and navigates to the correct target. And what's interesting about these particular results here is that if you look at end-to-end learning, if you look at the end-to-end reinforcement learning, you can see that the performance is quite poor, right? And it's interesting because this is an example where actually using prior information becomes very important. And it's also much more robust to noise, so in the pose estimate. So we actually build a real robot that moves around in your house, for example. Here's another example of looking at the pose estimation. So here you're looking at a pose estimation predicted versus the ground truth. And you can see this agent navigates in this virtual world. And as it navigates in virtual world, it tries to estimate the pose. It's trying to estimate the exact position, X, Y position and orientation. Right, and these are kind of architectures. Again, they are based on what we call the graph graph neural optimizers. They actually construct a graph-like architecture. Again, this is where the prior knowledge comes in order to be able to solve this pose estimation problem efficiently. And then finally, at the end, I just want to mention that we also started looking at building the semantic map. So when our agent navigates in this world, we can combine language. We can use instruction following, but we can also build a semantic map of the environment, right? So for example, where the chairs are, where the table is. And this is just another example of the agent navigating through the environment. And now you're actually seeing it's building the semantic map of the environment. So these little colored images basically represent different objects in the scene that the agent is basically finding. And this particular algorithm, we've just, again, my student just won another CVPR challenge, what we call image goal navigation challenge, by basically figuring out where the location of different objects are. And so when we think about all of this research, we also think about sim to real. So, when we look at these simulation worlds, the question is, can we take whatever we built and can we build it in the real world? And then there is obviously the gap. There is what we call the physical domain gap, right? Because the robot doing in the physical robot is challenging. There's also visual gap because in real world images look slightly different. And we've been looking at kind of like, trying to deal with the physical domain by looking at the actuation noise models, looking at the sensor noise models. There's also going to be a paper coming in arXiv that actually tries to leverage the dynamics, so going from the simulated dynamics to the real dynamics model, as well as in the visual domain. There's been a lot of work on image translation as well as policy-based systems, and we've been looking at actually applying all of these algorithms on the real robot. This is a little robot. It's called PyRobot. Again, it was developed by Facebook and was as a gift was given to CMU. So this is sort of an example of this little robot navigating in the real world in my student apartment. And you can see as it navigates, it's actually fairly accurately builds the representation of the environment. So it figures out where the walls are, it figures out what's the empty space, when there is no empty space. And, this is another example of kind of looking at the living room and building the map of the environment. And this is kind of the first step towards building these semantic systems that can understand what's going on in your environment. And obviously combining it with the language, hopefully will help us build much more intelligent systems. So as a final slide, how can we build systems? We want to be able systems that navigate autonomously, that can localize, that can plan, that can understand language. I can understand human speech. There is other aspect of it is what we call self-supervision, building kind of a robot that can in a self-supervised way, learn more about the environment, just in a way that humans learn. So let me stop here, and I just want to thank my students, amazing students. at CMU, and the work that a lot of work that I've talked about was actually done by my students. So thank you. And I think we still have some time for questions.
Yeah, we have some. We have 7 minutes for question. So, yeah, so we will have some audience in the chat room, and so if you have some questions, you can raise your hand. 大家可以举手问问题。我们还有几分钟的时间，大概会有一些问题啊。
Hello.
Yeah.
Hi.
Please
Can
go
I
ahead.
ask a question?
Hello.
Hi, Ruslan.
Hi.
This is Jun. I have a question. So, very nice talk. So I have a question about the first part of differentiable reasoning. So when you train the end-to-end system, do you need to construct some negative examples to backpropagate the signal, or I mean, like a pre-training type of technique people use in natural language processing?
Yes, so very good question. So I skipped some of those details. So we do use BERT-like language models as a pre-training step. So we rely a lot on these large-scale pre-training models. And the way that we're constructing, yes, we need, so we do need some negative examples. The way that we get some negative examples is because we actually have a set of, most of these data sets, they come with question and the right answer. So we know what the right answer is. And so what we do in many cases is our negative examples, when we do the top K retrieval, so we retrieve the answers, our negative examples become the wrong examples that we retrieve. So we don't need to construct them explicitly when we build the system. It just basically comes out, basically the answers that are incorrect become our negative examples. But here we don't need to do an explicit search for the negative examples.
Okay, thank you.
And to your point, you could probably improve these systems a lot, especially the multi-hop systems, if you had some labeled information for intermediate questions. So, like right now we don't use that, but potentially if you have more labeled information, particularly for these complex multi-hop questions, then that would help.
Right, yeah. Thank you.
Yeah. Okay, great. Okay, so Ross, so actually we are running a bit late. So because of network problem and also some other trouble. But sure. Anyway, we will collect all the questions actually from the audience, and also there are many users actually is online. So they will send to us many questions. We will just combine them and send to you maybe later by email. And yeah, okay. So I just want to say actually thank you very much for the excellent talk. So okay, thank you very much. And we probably will have to switch to another talk because another speaker is waiting, and she said that she have to leave maybe later. So
okay, sounds good. Thank you so much.
Yeah, thank you, Ross.
Thank you.
Yeah.
Bye.